Good afternoon. If y'all come in and find a seat. Thank you. I wanted to welcome everyone to the 50th incarnation of the Lunar and Planetary Science Conference. This is an exciting week. I'd like to introduce myself. I'm Eileen Stansberry. I'm the Chief Scientist at the Johnson Space Center and one of the conveners for this meeting. And we also have Louise Proctor from USRA, the Lunar and Planetary Institute. She's our other convener to this conference. I'd like to mention that we are having record attendance this year so far. Looks like we're on a good trend. The program is very exciting this year with a number of extremely interesting sessions. One logistical note that I'd like to mention to everyone is, again, like is normal for the Masursky Plenary, we do have to be out of here promptly so that they can restructure the room for the afternoon sessions so that we can keep on time. So they'll build the wall back up and all of that. So when we're done here, if everybody skedaddles out the doors in a timely manner, that would actually be very helpful. And now, so that I can make sure that we have plenty of time for this afternoon's plenary, although this man does not need any introduction, so it will be a very short introduction, we are honored this afternoon to have the only geologist to, as of yet, walk on the moon, Dr. Harrison Jack Schmitt.
Thank you, thank you, thank you, thank you. Thank you very much. Those of you who would plan to go to the moon someday, sit down. All right. We're going to do a number of things today. But first of all, traditionally, somebody needs to have a lunar ball. Okay. You know, back when I started that, they were little hard ones, but we've softened them up a little bit. What we're going to try to do today is answer a couple unanswered questions, and I've already cut out the last two items on this, unless there are some questions later, so that we can get through some of the more exciting parts of it. But first of all, let's pay tribute to this man, Neil Armstrong. Neil turned out to be the best field geologist on the moon until Apollo 17, of course. In 20 minutes or so, he collected a fantastic suite of samples, deployed some geophysical experiments, which has an interesting story behind it I won't try to tell right now. And we ended up, had we never had another mission, having answered, gotten some really significant insights. In the sample collection area, we found out, as Harold Urey suspected, that the lunar basalts were very old and had a significant range of ages, which has since expanded, of course. And that meant that the lunar basins were even older than the basalts. So right there, we knew the moon was going to be, at least in part, the record for the early history of the Earth. That was not clearly understood before Apollo 11, but it is clearly understood afterwards and now. The early we found the chemical age, mineral. Do you think these lights could be turned off of the stage? You're getting some glare off the screen, I think. Let me know if you can't read it. There we go. Chemical age, mineral eruptive diversity of the Myr basalts is quite extreme. There were 5 basalt cooling units in the upper 30 meters of the site, probably sampled by West Crater. There were 9 separate vesicle assemblages. If you want to know more about those, you read the first volume of the Lunar Science Conferences. It's under the innocuous title of Introduction. And 2 varieties, possibly 3 varieties of volcanic pyroclastic glasses. And in addition to in the sample collection, the idea of a magma ocean hypothesis was developed by Woods and Smith separately. The anorthositic fragments, differentiated source region for the basalt, the specific titanium-rich source area had to exist. And we also began to understand, thanks to Neil's very insightful decision to fill the rock box with regolith, what we sometimes call soil, with 100084, that the solar wind volatile resources of the moon were quite significant. From those samples and the breccias, the regolith breccias that he collected, we were able, I at least feel that we were able to determine that in the sample collection, we probably lost about half of the volatiles just in handling. From the time they were collected, the time they were distributed, and unfortunately very small aliquots to some of you and your former colleagues, we did lose quite a bit. So the actual concentration is maybe twice of what we have measured. In experiment deployment, we had the solar wind composition experiment, and for a long time, and even today, that represents some of the primary data that we have about the solar wind. Very high seismic hue of the crust indicated we had a mega regolith, and that thermal insulation was a very important factor in the later melting of the moon. By the way, when the moon started ringing like the proverbial bell in response to various impacts, that was really quite an exciting time. A very low seismic noise from the lunar interior, although there's some, and high precision Earth-Moon distance through laser ranging. Again, if somebody will ask a question about why did we select the experiments we did, namely a seismometer and a retroreflector, you ask that for questions. Now, for Apollo 17, these are the areas that we investigated. The stations are shown there. It's a valley deeper than the Grand Canyon, and really turned out to be probably the best site, other than the far side, for the last mission to the moon. And one thing we have to, I just caution you to remember that all the evidence points towards that valley being a graben produced by the Serenitatis impact. And that in turn, as we pointed out in our Icarus paper a couple of years ago, really does determine, that knowledge determines the relative ages, I think, of Serenitatis and Chrysium. We won't get into that today either. I wanted to, excuse me, that was not a live picture from the moon. I just want to point out what Ron Wells, my colleague Ron Wells, and his son have done in order to balance the colors of the pyroclastic deposit I discovered at Shorty Crater. Those are real colors based on what is in the photograph. It's not colorized in that sense. That information is in the photographs. It's never been pulled out before, and Ron and his son have pulled it out based on my real-time descriptions of what that color was, both the red, the orange, and the yellowish colors that you can see in that image. Some of you have not seen this before. I just thought you'd like to see it. And we're going to talk a little bit more, at least to summarize the pyroclastics. Now, this is a recent eruption in Hawaii. Had that eruption occurred on the moon in 1/6 gravity, this is what you would have seen. And you've that perspective you got to keep. You got to keep these perspectives. The moon is different, and so as a result of the fissure eruptions that we discovered in Sculptured Hills and also on the North Massif through radar and LRO images, we now know that the entire area, and we could see that to a great degree even in previous photographs, it was mapped as the dark mantle material. The whole area was once covered by a meter or two of pyroclastic ash. Again, a perspective that you need to keep in mind. Now, the units that I have tried to identify, and I think reasonably good, in the pyroclastic ash at Shorty, I'm not going to get into detail on this. There are 5 of them, and for a bunch of them, we have quite a bit of extra information. Just the depth range is shown on the left. I call your, whoops, what is that all about? There we go. Try that. Okay, we had some problems in putting these in the system. Yeah. Is the other side have? Oh, good. Okay, thank you. I forgot there was another side. Okay. Moving on, we do have a variety of exposure ages. One of the most important things to recognize here is the maturity index that Morris has put together has... you want to read these out loud for me? You know, there's a little bit of maturation in the upper unit, not much, but almost nothing in the lower unit. And I just put in terms of volatiles, one of the main volatiles in these ashes is zinc. There are certainly a lot of others, a factor of 10 to 100 times what we find in the basalts. And one of the things to remember is that there is clearly a lack of identified regolith horizons to go with that wide spectrum of exposure ages. But that's probably because all the impacts were occurring in ash, and so it was just redistributing ash. And it's going to be hard to pick out a regolith, an agglutinate in an ash that's made up of ash. So it's an important distinction, I think, to keep in mind. Now the sample locations that we got there in about a half hour of work, the only one that I missed and I regret greatly was the yellowish material right at the contact with the light gray regolith. And that regolith is what protected this ash from being incorporated like all the other ash was in the regolith of the valley. We were very fortunate in that having happened. And also, I think we've been able to determine, because of the characteristics of those units I showed earlier, namely that one of the bottom units have been overturned, whoops, that we can get some idea of what the structure is. That's the outline of the deposit. And there's the actual plane of an isoclinal fold, probably dipping about 45 degrees to your right. And then the 3 of the units are exposed at the surface, primarily because I think the axis of the fold is roughly horizontal, but the slope there is such that it would expose some of those units. This is a stratigraphic column that I put together some time ago, but what I really wanted to draw your attention to, many of you have seen that, is that in both the absolute ages that would determine isotopic ages for the top and bottom of the core, and in the exposure ages, we have evidence, strong evidence, of a very long period, 150 years or so, of pyroclastic eruptions that produce this ash. Also, now I think we have a pretty good understanding of that there has been migration of volatiles out of the ash into the protective light gray regolith lying above it. In fact, the volatiles in the regolith have about twice the concentration that they have in the ash. So there has been volatile migration. Now, I point out also that there's I reported about a ½ centimeter of regolith on top of this exposure. That always bothered me, it always bothered me that we were, most of the time when you're reading the literature, that the Shorty Crater was 17 million years old. That's not enough regolith for 17 million years. There are many ways to say it should have been more. And so I think we finally have figured out that the Shorty Crater has about a 3 million year age. Its exposure age, total exposure age of the Unit 5, the top unit, was about 24 million years. But in looking at 74255 Boulder, it now is pretty clear it was re-excavated. It's gone through at least 2 major impacts. And Shorty just re-excavated it, put it on the surface, and Oyster and Company have come up with a 17.8 million year first exposure of that sample. And actually, there's another sample that has pretty much the same information on it. And about a 3 million year second exposure with an estimate of 20 centimeters of that boulder, that highly fractured boulder, having been eroded between as a result of that second impact. And Gaswani and Lai have confirmed that with particle tracks. So we have 2 different types of age dates, exposure age dates on those rocks, on that rock. And so my conclusion there is that we're dealing with Shorty being about a 3 million age. Now, what about the other impact, and particularly the impact that provided the light gray regolith protective cover of the ash itself? And there, I think for some strange reason, I've named this faint crater Fitzgibbon. Some of you will understand that. But if you look carefully, you can see that the boulder is visible on the rim of Shorty, and that low part of the rim where we actually did our sampling is low in part because of the pre-existing crater. That crater, though, is something like 3.5 billion years old. So you have to imagine how much has gone on since then. Now, also from the ash, we have a chondritic source for our near chondritic source for the pyroclastic volatiles. There's the existence of deep volatile reservoirs, which would be inconsistent with a whole moon magma ocean, in my opinion. The volatiles are greatly distinct from the magma ocean upper mantle, which is the source of the Maria, and pyroclastic magma derived from a garnet-bearing source, as well, as Clive has pointed out to us. Rare earth elements in the ash are consistent with derivation from a chondritic source, our near chondritic source. Siderophile elements likewise. Now, the new thing that I ran across in my latest synthesis of this is that the del nitrogen 15 is a plus 13 in the lower units of that pyroclastic ash. That seems to me to be, if indeed you agree, or we can agree that the volatiles are probably primordial, that we're looking at what the solar wind isotopic ratio for nitrogen was at the time of accretion. More on that will come later. And I just might point out that it's comparable to the class in the instantite chondrites, which also have very similar isotopic ratios overall to the moon and indeed to the Earth. Okay, way back when I started working with Gene Shoemaker, who was one of Hal Masursky's bosses, as Gene was my boss. Gene was talking about the lunar regolith contains a history of the sun. And we spent a lot of time debating that, talking about it, and indeed in the field geology experiment for Apollo 11, we added core tubes. They weren't very well designed. Hoover Mackin and recommended core tube design, and we had forgotten that the moon, well, we didn't know at the time how incompressible the lunar regolith was, and so you couldn't you couldn't drive a flanged core tube very deep into the surface. But the idea was there. And the rest of most of the rest of my talk will be trying to get into this story of the history of the sun. The deep drill core at Apollo 17, of course, is the best one that we have in terms of overall quantity. It's a complete 268 centimeter core into the regolith, and with quite a number of units exposed in that. Again, determining the lithologic stratigraphy of a core tube in the regolith it results in a lot of judgment, but I think this is pretty good. And probably coincidentally, we had a lot of data related to each of those units, particularly in the nitrogen isotopic composition. Also important to recognize that within that, this zone T is probably camelot ejecta. I've looked at the lithology of that. It's essentially identical to the lithology of the rocks around Camelot and at Camelot. And so if our 500 million year age for Camelot is correct, that's a topographic diffusion age that Caleb Fassett put together for us, is correct, then we do at least have some age tie into that core. We'll deal with that more later. This is a work in progress. I'm not going to spend any time on it, but I think within the lithology, we're going to be able to identify the source craters for each of the units in that regolith. We already, of course, the zone T is from Camelot. X, Y, and Z, I'm pretty confident because of their very distinct lithologic character, have come from the three craters that you see listed there. S, the surface probably has crater cluster regolith in it. The others we're going to have to keep working on. Whether Horatio contributed or not, I'm not sure. But the thing I want to point out to you now is to compare the maturation index of Morris with the nitrogen Del 15 nitrogen data that was put together by the Clayton's group at Chicago. That's what you get. So clearly, maturation increases, linearly increases the Del 15 nitrogen. Now, I think that's new information. I don't think anybody had ever plotted these two against each other. And that means it may be very useful to us for other reasons. The slope of that curve is a plus 1.22 per mil. S is an outlier, and we'll talk more about that. It's really an outlier. And I'll just, as a heads up, all the surface regolith of Apollo 17, and I suspect of the rest of the moon, are going to be outliers to that curve. Now, if you correct for that maturation, correct the Del nitrogen 15 for that maturation, the lower units of the curve all come out at about 105 plus or minus 5. And I'm suggesting to you today that was at that time at least the nitrogen isotopic ratio of the solar wind, the Del 15 ratio. Now what do we do? So Del 15 for the zones U through Z, the lower 7 zones, corrected by it should be plus 1.22 MI, are at 105 plus or minus 5 mil, indicating a constant solar wind, at least for that period of time during core deposition, and prior to 500 million years. Just keep that in the back of your mind. Whoops, a little slow on the uptake here. Sorry. Well, anyway, you saw the circle around the upper 2 units. They don't fit. Now this is just for the sake. Remember the. There we go. Now, remember my del nitrogen 15 for the lower parts of the pyroclastic ash was plus 13. If you take that age through the zone T, which is 80, corrected at 89, you get almost, that curve intersects up there at about 100, around 100, minus 100 per mil. I'm not sure that if this curve really has any significance, as you'll see in a minute, but it's consistent. But why is corrected del 15 for Camelot zone T equal to minus 89, and for the surface zone equal to minus 38, very different than 105, and we'll try to answer that question. Now I'm going to take you to the sun. This is a generally accepted, as I understand it. I'm not a solar physicist. I don't play one on TV. And I don't know anybody who is except Len Fisk. And he assures me he only deals with the coronosphere. But so that's sort of the last 4.5 billion years is what we're going to look at here now for a while. If you believe that 105 plus or minus 5 per mil figure, then this is something like this is what happened way back when. Is that we had a fairly rapid rise in that first, let's look at it again, that first part of the sun's history, a rapid rise in the, a change in the nitrogen ratio. And now that probably may not be a straight line curve. I just don't know. I don't know enough about the physics of the sun to say, and we'll try to learn. But what we have, of course, from the deep core is that at least for some period of time, probably my guess is around 1 billion years, we had a fairly constant solar wind ratio. Now, does it help to explain the 89 and minus 89, minus 38 of the two zones if something has changed since about 500 million years ago? Let's talk about that a little bit more. Now, before we do, though, I want, by the way, and I understand there's a session that's leading off with data from Genesis, and we'll have to go there and see what they say. But this is the data from Genesis, is that the current solar wind is a minus 407 plus or minus 8 per mil. Major change required from the time of accretion. The deep core data just contradicts this. That's all I can say. Now, there is a complication in using del nitrogen 15 solar wind values to evaluate surface regolith units in the deep core. The Apollo 17 upper regolith samples uniformly have positive values versus negative values in the lower units of the deep core. And there's a plot that shows you the difference. And strangely enough, a line through S and T pretty much is close to what you would expect all of these to have. So that slope is plus 2.07. And I hope to be able to use that sometime in the future to get depositional ages for the units in the deep core. I'm just not happy with what has come out of that analysis so far, so we won't talk about that today. Now, nitrogen 14 might concentrate downward relative to 15. There's a cold sink at minus 80 centimeters. I think it's minus 20 degrees C that is stable. And the cold sink would move upward with each ejected deposition, but then stabilize again. And you can imagine that 14 might migrate relative to 15 to that cold sink downward. It's currently in zone U. Here, I'll just show you this. That's where they were at various periods of time. I don't think that's what happens, and here's why. Downward migration of 14 relative to 15 is not occurring because of the highly variable measured 15 ratios with depth, and they are consistent when corrected. That is not what I would imagine happen if you were migrating 14 depth. You wouldn't see that kind of consistency. Zinc concentration also varies inversely with maturity. And zinc is one of the more active volatiles in the regolith. So it's not migrating. So if it's not migrating, I doubt if anything else is. However, I just remind you that we do see evidence of upward migration in the pyroclastic ashes. And that's something I think to keep in mind when you start dealing with volatiles in the regolith. Now, a more likely explanation may be an increase in the rate of regolith maturation at about 500 million years by a factor of 1.7. That's comparing those slopes on the previous graphs. And that could explain the maturity data that we see. Higher rate of maturation would increase regolith del 15. This factor of 7 brings zone T, Camelot, to a del 15 of 105. And that's where I got it, actually. I was looking for a way, what would it take to make T at 105? Because it's over there on that curve that the other zones are. An increase in solar wind, del 15, at 500 million years could also be involved. You can change the slope of those curves two ways. You have two variables, you can change it two ways. And it may be a combination of both. I don't know that yet, but we're going to keep looking at it. There are the two curves, and do zones T, S and T indicate an increase in solar wind, del 15, or an increase in the rate of maturation, or both? Just to keep you abreast of what I'm talking about here, those are the two curves that we have. They're not curves. Now, and the change between the two is that factor of 1.7. However, something happened to the solar wind about 500 million years ago. I'm finding that an inescapable conclusion. Increase in solar luminosity and or a change in the del nitrogen 15. What else happened in our neighborhood of space 500 million years ago? The Cambrian explosion and diversification, estimated at about 550, 540 million years ago. Warmer Earth? What you think about it? And with that, I'd be happy to take any questions after we look at Hal walking down the hall. No questions. Okay, let's clear the room.
Okay, state your name and affiliation.
Ryan Ziegler, Johnson Space Center.
Hey, Ryan.
Hey, Jack. So I was wondering if you could talk a little bit about how the sites were selected for the missions, especially on the later missions. Did what you were learning about the samples from the earlier missions inform where the later Apollo missions went?
There's no question about it. There was quite a variety of inputs, of course, to site selection. The Apollo 11 site really was determined by Apollo 10. And Apollo 10 site was determined by Apollo 8. And that's a longer story than you want to hear, but the crew of Apollo 8 thought that looking at the surface from 60 nautical miles for their site, which is the farthest east Apollo site, indicated to them, at least at the best they could with 10 power resolution, as a good place to land. And so I suggested to Tom Stafford, who was Apollo 10 commander, as well as George Lowe and others, that, well, maybe we ought to slip, since that looked good, let's let the crew look not only at the next site, but then because they're going to be up there longer, they can look at a third site. And that gave us some flexibility on when we launched the actual lunar mission, which turned out to be Apollo 11. And so once they agreed, finally, mainly because of Jerry Hammock. Anybody remember Jerry? He was recovery chief in the Flight Control Division. Anyway, Jerry said, hey, we get a daylight landing if we change, and he always wanted a daylight landing. People forget Apollo 8 landed in the dark, just before sunrise. So that gave us Apollo 11. And once you had the data pack for Apollo 10 settled, you pretty much were going to go there for Apollo 11. After Apollo 11's difficulties in landing where we thought they should land, it was decided we needed to learn how to do pinpoint landings. And of course, my geology suggestion was, let's pick a crater someplace, get close to it. No, let's pick Surveyor. And it turns out that was the right decision. It was not the geological decision, but it was the right decision. And so everybody focused on landing near Surveyor 3, and that determined that site for Apollo 12. Apollo 13 then was the first one, and I also had the first really intensively trained crew, Jim Lovell's crew, in the new simulation-based field training that Al Shepard and I put together. And we decided that the thing you wanted to learn something about was Imbrium ejecta, since it was so pervasive everywhere. So Frau Morrow site was selected for 13. Since 13 had its incident, 14 was targeted there as well. And then we got a little more ambitious. We want to go farther north, get near the Massifs, get near Rill, things. So Apollo 15, that was determined. Now, just because I can go through that list doesn't mean there weren't a lot of conversations about site selection. Every mission had its list of sites, and there were plenty of scientists and engineers sitting around arguing the pros and cons. But the final decisions were made pretty much like I say. In 16, Cayley formation was always important. Hal Masursky talked about Cayley, Gene did. Everybody who mapped the moon one time or another was interested in the Cayley formation. And that's really what we thought we were going to get to with Apollo 16. And as some of you know, I think we did. It's just we didn't recognize it at the time. I think what we have there are pyroclastic deposits, lithoclastic deposits, much like I think we've demonstrated exist at Apollo 17. And then Apollo 17, and once they rejected my idea of going to Tsiolkovsky, it was pretty, and once we figured out how we could land in a deep mountain valley like Taurus Littrow, it was an ideal site. 3 dimensions, many different varieties of materials, as we all know, and it really was a joy to be there and to explore it. Thanks, Ryan.
Larry Nittler, Carnegie Institution. Thanks for a very interesting talk. In terms of this very interesting nitrogen trends you're discussing, we know that there's a diversity of nitrogen isotope compositions among different chondritic materials. Could these different trends just at different times, at regolith forming at different times, rather than the sort of physically dubious idea of 30% change in the solar wind isotope composition, perhaps be a change in what materials were being delivered in impacts to the moon at different times from different parts of the asteroid belt?
The answer is probably yes, could be. When you get back into the chondrite formation time, God knows what was going on within the solar nebula. But there may be ways in which you can start to pin it down, beginning with what we have found here, at least within this one core, and within the pyroclastic glass. At least we have a number, if that 13, plus 13 number for the volatiles in the pyroclastic ash is a good number, that can be, I think, very useful to us as we start to look at the final condensation of the terrestrial planets in the solar nebula. It's going to take some time to think about it. It's, again, trying to think out of the box and broaden our perspective here a little bit.
Back to back.
Don Burnett.
Hey, Don.
I know Jack from 47 years ago. I'm also the Genesis PI. I don't think the solar wind composition changed, but let me come to your rescue. I think what you're saying in terms of Delian 15 as a stratigraphic marker for lunar layers is a good idea, and it'll probably work. We can go into the details you want to see. You're on the right track. Forget about the sun changing. Stay with lunar stratigraphy, and you've got something good.
Well, Okay, I will, but I don't know. I can't stay with lunar stratigraphy at 500 million years if the stratigraphy is going to change on me. So we got to figure out Don, what's going on there. Next.
Hi, John Gruner, Johnson Space Center. Your current life has you as a member of the user advisor group on the National Space Council. So I'm wondering, what do you think about that group? How are things working between the different personalities? And what are you guys wrestling with right now to get us back to the moon as soon as possible?
Let me answer that last question first. I think what we're wrestling with is getting some sense of urgency in NASA. And that came out in spades at the last user advisory group meeting. Many people were very uncomfortable with. Basically, NASA has a charter. The president has given NASA a charter to get back to the moon. I think the president and the vice president feel there's a significant geopolitical urgency to do that, but that we do not sense that NASA has that same sense of urgency. So that's I think where we're at, and frankly, things don't seem to be moving very fast to get us back to the surface of the moon.
That's sad.
Other than in the commercial sector, there's a lot going on there. Yes.
Yes. Ben Hoefnagels from Big Bang Meteorites. I was wondering, do you have your own lunar stone at home at the mantelpiece?
No, not at all. They belong to the taxpayer, and the best that NASA's ever done is to provide each of the astronauts a plaque in which there's a small piece of the moon that you can donate to an institution, and called the ambassador plaque, or ambassador to space or from space. I can't remember. Anyway, believe me, I don't have a lunar rock on my mantle. Yes.
Hi,
I have a Canyon Diablo meteorite.
Hi, I'm Rebecca Boyle. I'm a journalist. I'm writing a book about the moon. You were mentioning that you wanted to talk about why you did the experiments that they did on Apollo 11, the laser ranging experiment and other geoscience experiments.
You want that history?
Yeah, I want to hear that history.
We were, in 1968, the President's Science Advisory Committee asked NASA, and namely JSC, Johnson Space Center, then the Manned Spacecraft Center, to make a presentation to them on what their timeline was, what their detailed plan was for the first landing on the moon. And they not only wanted that done, but they wanted astronauts to make the briefing. And so Buzz Aldrin and I were called into Al Shepard's office and said, you guys are going to do the lunar part of this. And of course, Buzz, being the orbital mechanics guy, took care of all of that part of it, and I did the lunar surface. And I also knew from my attendance at the Configuration Control Board meetings that George Lowe chaired that he was extremely concerned about two things, mainly, one thing, weight of the lunar module, and hover time that comes from having too much weight, you lose hover time. And that, to me, put the overall ALSEP at 300 plus pounds at risk of ever flying on the first mission. And so when I was putting that briefing together, I came up with an alternative suggestion, and that we fly a much more limited geophysical package, low weight, and with the two experiments that everybody I could talk to in the geophysics world, Frank Press and others, Gene Simmons, said they ought to fly. One was a seismometer, and one was a laser corner reflector. And I presented that to George Gilruth in our pre-briefing for the Peace Act, and it was not well accepted by the science director, as you might imagine, as an alternative, but Gilruth said, we're going to present that to PSAC, and that sort of is where it ended up, was the development, very rapid development of those two experiments. Of course, the seismometer was already under development because of the ALSEP, and all we had to do was give it a temporary solar power source. So that's why you had those two experiments on Apollo 11.
Thank you very much.
Is that it? Thank you.
Thank you.
And with that, if everyone can exit so that we can reformulate the room for this afternoon session. Thank you very much.